Okay, how about now? Oh, yep, now we got audio. Glad I thought to check that before I really got going with stuff. Obviously, I'm not a professional streamer, so I'm not as quick with it. With getting like everything kind of set up and ready to go before I'm ready to go. Cool. We've got audio, we've got video, and we've got some homework to do. So let's do it. Okay. So this is just the disgusting amount of libraries that I've imported for this notebook. This is my data set, and I think I have since made another one so I can make an EDA2 or EDA3 journal. This is a function that one of the instructors actually wrote. I didn't write this. Claude Freed, I think is his last name. His first name is definitely Claude. If you know what variance inflation factor is, if you're like a stats person, that basically spits out the variance inflation factor for like every variable, and then I'm passing in the linear regression model. But that's not actually doing it. This is just the function made to do it. Okay. Convert age to an integer. Good. There's not a whole lot of use in going through all this because it's all going to be like kind of changed later on. So this is our first really like reliable visualization. The labels are kind of crammed in there, but this isn't going on a presentation, so it's fine that it's like a little ugly. It still kind of shows me what I want to know. So at first glance, looks like bathrooms. I'm looking for stuff that has like a linear relationship. So bathrooms looks like, generally speaking, like the more bathrooms you have, the more the price goes. On all of these charts, the sale price of the house is on the y-axis. Square foot of living looks like it has an even stronger linear function or characteristic or whatever. Floors is a little odd. But that kind of makes sense. I guess there's not a lot of people that want to buy like a 3-story house. That's a lot of stories to take care of. Square foot above, this means like above grade, so the square footage that's above ground. So the more square footage you have above ground, the more valuable the house becomes. I don't know that it really matters. That might just be kind of like statistical noise, because like the more square footage you have, period, the house is probably going to become more valuable. Yeah, as you can see here, square foot of just living space in general. So this is including above and below grade. This is really interesting to me that you have like all these super high valued houses on really tiny lots, and then it kind of diminishes where the bigger the lot gets, the less valuable the house gets. And I don't know if it's like farmland or what. Like maybe these people are all in like really nice neighborhoods, and so they're just kind of like jammed in there like Lego bricks. I don't know. This is for Kings County and like up in Washington, like around Seattle in that area, by the way. Square foot above grade, square foot basement. Again, we're seeing like a pretty similar thing going on with square foot basement above grade. We've got a little bit of a funky thing right here, kind of like we did with square foot lot, but whatever. The year that it was built doesn't seem to have a huge impact on it. You got a few right here, but I can count that nearly on one hand, so I feel like that's more outliers than anything else. Square foot living 15. So this is like the average square foot of the nearest 15 houses. And same thing for the lot. So it makes sense that we're seeing like similar patterns with the house itself and then the nearest 15 houses. Like it would be weird if square foot living 15 had this shape instead. Like if it was like swapped, but it's not, so whatever. Age and day of year all show similar pattern to year built, which makes sense. Ooh. What's really interesting, not that this shows linearity, but the age of the house, that kind of makes sense. That might not be as interesting as I want it to be. So the age is like the current year minus the year that it was built, right? So you're seeing like an opposite pattern. It's like the exact opposite. So we can have these same two outliers here. So this house that was built in 1900 is the oldest house. So this is in days, by the way, not years. So it's 40,000 days old. So that's, I am not a mental mathematician. So 40,000 divided by 365 days a year is 109.6 years old. And it doesn't look like its price has changed a whole lot. Or I guess that's not the price when it was built. So that actually, it would be the same price. That makes sense. So that's interesting to see that it's like kind of just like a mirror image, but that also means that neither one of those features are probably all that useful. The day of the year is like the day of the year it was sold. So like January 31st is going to be in there as 31, but then February 1st is going to be in there as 32, and then February 2nd be 33, and so on and so forth. So it's a 1 to 365 scale, kind of indifferent to like what the year is. This is just like where in the year, whichever year it was sold. Bed bath ratio. I'm gonna clean my screen off a little bit. Y'all can't see it, but I can. Bed bath ratio is, so this is the ratio of bedrooms to bathrooms, showing a similar pattern to the square footage of the lot, interestingly enough. What about bedrooms? Bed. Kind of similar pattern to bed, but not at all similar pattern to bathrooms. So that's curious, if nothing else. The level ratio is... What is the level ratio? Good thing I wrote myself a data dictionary. Oh no, I didn't want to. Fuck. Okay, whatever. How do I make a new tab? Bruh. I just want a new tab. I don't want to split it. Bro, I want a new tab. Oh my, I can't believe I'm about to have to Google how to make a tab in VS Code. Okay. Make new tab, VS Code. Double click it instead of single clicking on it. Wow. That did nothing different. Okay. Bro, I'm fine with having like difficult problems to solve. This type of shit though just like drives me up the wall. Anyway. Okay, that's saying to create just like a completely brand new tab. How to lock a tab in VS Code, how to open a file in a new tab. I don't want to do it by default, dude. I just want to do it like when I want to do it. Oh my god. Cool. That's incredibly annoying that I have to click and drag it instead of just clicking on it, but I don't know, maybe if I right click it, open to the side, open preview, open with, reveal, blah, 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 blah. I am going to fucking egg the Microsoft headquarters for this because that's super annoying. I don't even know where the Microsoft headquarters is, low key. I didn't mean that. Please hire me someday. Maybe. I don't know. Anyway. Okay, so level. I know it has something to do with the amount of floors. Ratio of square foot above grade to below grade. Okay. So this would mean that for every 100 square feet above grade, there's 1 square foot below grade. But this would mean that nearly for every square foot above grade, there's square footage below grade, which is weird to me because you would think like, I don't know. I've never bought a home before, so I don't know if maybe having a bigger basement would be an attractive thing. Follows kind of the same pattern as the bed bath ratio though. Relative living space. So this is the difference, I think. Yeah. Between a given house and the other 15 houses around it. So this is the ratio of this feature to this feature. So that follows a linear pattern, obviously. So that is probably going to be a reliable feature. Relative lot size is the same thing except just for lot. So you can see these houses are like smaller than the others around them. So obviously they're going to be cheaper. It's still weird to me though. This is like showing the same pattern as like the lot square footage over here did. Obviously you can't have like negative square footage, but you could have like a negative difference. So that's why this goes past 0 and this one doesn't. But it still has that huge spike like right near 0. So it's not necessarily that houses that are bigger or smaller are worth more, but or lots that are bigger or smaller are worth more, but it's like lots at the same size, which is like weird to me. Level difference. So this is like this feature, but this is just the difference. It's not the ratio. So this is like total square foot above grade minus total square foot below grade. So that looks like it has a little bit more of a linear pattern to it. But anyway, so this is all pretty much everything from square foot lot 15 back is from the original data set, and everything here is extrapolated from that data. So like I engineered it. So like I did some coding in the EDA1 journal over here where I, did all this math and created new columns with this new data based on the existing data. So this is the same features just visualized on KDE instead of a scatter plot. So this is not really encouraging to look at because I don't see anything here that looks remotely normally distributed, which would be like a normal bell curve. Square foot living 15, level difference, square foot above grades, square foot living seem possible. Bedrooms, bathrooms, floors, conditions, and grade don't really, those visualizations don't really mean anything because those are categorical variables, not continuous. So you only have like 1 or 2 or 3 floors, right? Or like the condition or grade are set on specific scales. It's like 1 to 5, 1, 2, 3, 4, or 5, and same for grade. It's like 0, 1, or 2, or 3, or 4. So it's like it's not on a continuum the way square footage is. You might have one house that's 1,000 square feet, one house that's 1,001 square feet, and another one's 1,001.5. So that, because that you could get super granular with it down to the inches if the data was available. So that sort of stuff makes a little bit more sense on a histogram like this, which this is basically a histogram just with like a KDE line. This is weird, man. This is not encouraging, because I'm gonna have to do some really weird math stuff that I'm not super confident with to make this data normally distributed, to make it reasonable to pass into a linear regression. But as we go through this notebook, you're gonna see where I pass it into the linear regression anyway, just to see what it spits out. And then we're probably gonna start a new EDA journal, and that's where we will start doing the weird math stuff to get a better linear regression model. Okay. So here we're doing some one-hot encoding. So like I mentioned earlier, we have those categorical variables. And so basically what this does, man, I'm really tempted to just clear all the outputs and rerun all the cells, but that might take fucking ages. You know what, we're gonna do it anyway. Clear outputs, we're gonna restart the kernel, and then we are going to run everything above this cell, and we're gonna wait like 20 minutes for that to happen. Not really 20 minutes, but this is gonna take a while. Normally it would only take like maybe 60 seconds or so, but I'm streaming right now, so my computer's kind of gasping for air at the moment. You can see I can't even scroll smoothly right now. We're still importing all our libraries. Okay. Good. This is just declaring some variables and functions and stuff, so of course that's not gonna take a huge amount of time. This is a little bit more processing heavy. There's a lot of like stuff that the computer's actually having to do here. This thing has been a fucking game changer when I'm playing VR on my Oculus, because like when you're in the Oculus, right, it's covering your face, so you can't really like throw a glass back, but with the straw here, boom, you're like right there, good to go. Looks like we're still running. Oh, we're doing, yeah, that's gonna take a minute. This is the distribution plot with KDE lines. Yeah. So the reason I'm doing this is because there was like, you can see here where it says like what order the cell was ran in. And last time I did this notebook, it was just like all over the place, because that happens. You'll like run a cell and you'll go back and edit something and run that cell, and I just kind of wanted everything to go top to bottom nice and smooth. So now we have our data. It's been one hot encoded. So this like is basically when you have categorical data, you have to create a new column for every category, and you give it. You can see it. They all have like the same prefix. So this is like this whole column is any record that has a condition of 1.5. So the condition's on a scale of 1 to 5, and I guess you can have half steps. Same for grade, obviously. So if that is the condition of this house and it's going to have a 0. If it's not, then it's going to have a 1. You can't see all of them right now. It's like condensing. You can see like the ellipses here. There's a bunch of other of these stuff like in here because there's like a ton of them right now. So it just can't fit it all on the screen. There's at least one in every row. So or like for all the out of all the condition columns, for every row there will be a single 1 and everything else should be 0. You can see there's a 1 here also, but that's for grade, not condition. So there'll be a 1 in every row for every series of columns, if you will. And I did do drop first, right? Yeah. Okay. So all I did here was I made separate data frames with the categorical features. One hot encoded them, dropped the first one because you always have to drop the first column because you can't. It'll mess up your data because if you have like, say if you have like a categorical variable and it's like 1, 2, or 3, if you have like those 3 columns and you have like a 1, 0, and a 0, 2 of those columns are basically telling you the same thing because you only need 2 columns to like infer what the other column is. So if you have like 3 columns, you drop 1, you see in one row that it's a 0 in both columns and it must be a 1 in the other column. So you have to drop one of the columns to avoid getting like duplicitous data. So now we're going to run the linear regression. Wow, that was really fast. I'm going to go ahead and run this and we'll go back and review the model. Okay, so I don't think I created, yeah, I want to make this into a new CSV so that I can start a new journal and visualize and model with this. But we're going to check it out first real quick. So our R squared basically tells us what percentage of the outcomes is explained by our data. So only 60% is pretty weak. I'd like to see like 70, 75% probably. Also, this is probably misleading. Well, I don't know. It says our adjusted R squared is the same. So like the more variable or the more features you have, which obviously we have a ton right here. Looks like a couple, like maybe a dozen or so. So adjusted R squared is R squared, but penalizing for like the amount of features that you have. So the fact that the adjusted R squared is the same, despite having like a ton of features here. When I say features, each columns, or these are all features. That's suspicious to me. I don't remember what the F statistic means. I should probably look that up. So our p-values, pretty much anything over 0.05 you can throw out. So square foot lot, I'm gonna make a markdown here. No, I don't. Oh my God, Okay, we're gonna look at square foot underscore lot. Square foot above. Square foot basement. Year built. Square foot lot 15. Age. Day of the year. Relative living space. Whoa. Wow. I said whoa because I was pretty sure that was going to be a really useful feature. I'm going to go back and kind of look at these in relationship to the scatter plots. Square foot lot makes sense. Square foot above grade, that's weird. Square foot basement, also weird. Maybe I'm gonna put asterisks here to mean see what happens when I just like move out the outliers. Because like square foot basement, you see you have like this straight line right here, which might be data input typos or like whatever. I don't know. It's odd that this is kind of like generally scattered and follows this kind of thing, but then we get this like column right here and like right near 0. Kind of suspicious. Year built. That makes sense. Square foot lot 15. That makes sense. Age, that makes sense. Relative living space, that's very odd. And relative lot size, that makes sense. Cool. And I'm going to put this in my data dictionary too. Maybe I'll call this a data journal. I don't know. First, Linreg model. And now I want to know about my variance inflation factors, which I don't even know how to, oh good. See, I took notes. I was gonna say I don't know what these numbers mean, but now I do. So for your variance inflation factor, what this is checking for, by the way, is so by the way, p-values, what we were just looking at, is basically how like statistically significant the correlation is. So like a p-value of 0.447 is, let's round that up to 0.5, and what that basically means is there's like a 50% chance that the data output is not random chance, which a 50% chance of that is just random chance. So, or like there's a 30% chance that like the answer to your question, if you will, is wrong. Or you got like a false positive due to just like randomness in your sample or whatever. So that's what your p-value is. And obviously we don't want to mess around with features that are basically random. Random might not be the right word there, but point being, they're not reliable features to look at. Wow. Okay, so with the variance inflation factor, 0 to 5 is good. 6 to 9 is like questionable. Anything 10 or above, you just like throw it out entirely. There's a lot that's like bizarrely inflated. So we're gonna go variance inflation factors, and we're just gonna paste this in here. So we're gonna say this means keep them. Or we'll go good, meaning it is less than or equal to 5. And then this is going to mean maybe, which we'll call that like 6 to 9. I don't know why these colors are acting so, oh, it's because the asterisks, I guess. Anyway, and then we'll do this for no good. So, I don't like how I wrote that. X is greater than or equal to 6 and less than or equal to 9. Yeah. And then X is greater than 10 or equal to, greater than or equal to 10. So much. I'm gonna put like 4 on these infinities. That's kind of insane. I'm really like wondering if like this is because the data is just like shit, or if it was me, if I did something weird. So this is good. This is very bad. This is very good. This is ultra bad. Ultra bad. Ultra bad. Okay. So based on this, we would be keeping age, I lost my train of thought. Yeah, age, day of year, and the level ratio. And based on this, Whoops. So, oh, okay. This is everything that has a p-value greater than 0.5. So, what I want to know. Oh my god, that's so much. I'm so lazy, like I would rather like spend an hour coding something that would take me 30 minutes to like write manually. But we're just gonna write down everything that is not garbage. Bedrooms, bathrooms, square foot living, I'm sure there's like a method I could call on the stats model thing that I ran to get like everything, you know, with a p-value of like a certain whatever. But I don't feel like Googling it right now. Besides, sometimes going through your data manually helps you notice things that you wouldn't otherwise. Square foot living, already got their floors. What I'm worried about is that there's a lot of these that have like awesome p-values. They're basically 0, but the variance inflation factor is like through the fucking roof. So that's not awesome. But I will be able to look at, you know, if I get a list of the good stuff based on p-value and the good stuff based on variance inflation factor, maybe I can find some stuff that's good for both. Eyeballing it right now doesn't look like there's going to be anything. That was square foot living 15, not square foot living. Date of year. Bed bath ratio. Yeah, so this is everything with an acceptable p-value. I probably should have just written this all in one line, but I wanted to be able to read it, so that's okay. This is pushing P. all this stuff here that I was looking at, that like it looks linear on the scatter plot, but it has a massive p-value, so that means that, or I think that means that there's probably some funky math stuff we can do to salvage it, like log transform it or something. Square foot placement and relative living space. Relative, whoops, I don't know why I did that. I'm tempted to make this like nested in this list, but not for now. We'll run that cell so we have those variables available. So that's everything that's quote push and P. How does this work? VIF dict. So, whoops. Come on. Nope, it doesn't know what the fuck that is. So what we're gonna do is we're gonna go here, make it a cell. This is now our VIF dict. Normally I would use an underscore, not camel case, but I already have VIF dict in that function, so I'm just trying to keep everything copaesthetic. So for, whoops. For thing in VIF dict, if thing dot value, well, let's see if that works for first. Thing dot value. Nope. Unexpected indent. What are you talking about? Oh my god. Okay. We're just gonna have to do this manually. So we don't want this. Don't want any of this. And we don't want any of this. You see what I mean? I could have just done that initially, but I was just really wanted to make a for loop for it. But dealing with like those .inf values are not super convenient. So we're just gonna do this. So age is not here. Day of year is push and P, and it has a reasonable variance inflation factor, so that's good. And so does level ratio. Awesome. That's where we're already at. Okay. So we're just going to push in this. We're just gonna make this a list because it doesn't really matter what the VIF is at that point. That's way less of a mouthful than variance inflation factor. I don't have to talk like a nerd, so we're just gonna call it the VIF. Kind of like Vim. Make that a list. We don't need this necessarily, you know. Yeah, that's this list right here, right? That's correct. So we don't need that. So we're going to move this cell down here just so it's a little bit more linear, not in the mathematical sense, but like I like everything in the notebook to kind of go down the line. We don't need this really, but we are going to do some markdown here just to report on our observations. Okay, so items in push-in P list show acceptable P values, while maybe P items in maybe P show unacceptable P values. This is gonna bug me. They visually appear to show a linear relationship on the scatter plot. So they should be further investigated and perhaps transformed for a better fit into the OLS model. That's ordinary least squares, if you're wondering. While items in push-in VIF are the only items that show acceptable variance in Flatiron factors. So it's age doesn't make the cut, day of year, and level ratio. Indicating good confidence in these data features. That's insane. The fact that there's that many things with a variance inflation factor above 10. But anyway, so what we're going to do now is we're going to try to remember how we did that. Okay, so it makes a new tab automatically that time. Okay. It's gonna take forever to load, too. You don't have to run the book, you just gotta load it. It's fine. It's just text. Saved there already. PD read CSV path. This is what I'm looking for. We're going to go back to EA2, and what we're going to do here is we're going to make a new CSV file, and we're going to call it I want to know that it's one hot encoded. I just need to be able to call it. I don't need to read the name. Let's see. One hot one. That's what we're gonna call it. So we should see another one of these guys pop up here, right over here, when I run this cell. I see it. Woohoo! Okay. Cool. So I'm going to save this. we're going to probably keep that open for now. We can close that, and we're going to create a new IPYNB file. I mean, I know the language I want is Python, but I don't want I'm going to Google how to create new IPYNB in VS Code. Oh my God. Like I said, I don't mind like doing like hard coding problems and like math stuff and whatever, but like I just need to create a new file, man. The fact that it's like so complicated, or like not even, it's not probably not complicated, it's just like not obvious, and I have to like spend time doing this nonsense is annoying. You can create a Jupyter notebook by running the Jupyter create new notebook command from the command palette, or by creating a new .ipynb file in your workspace. Okay. I don't want this. What is the command palette? That's what I would like to know. Control-Shift-P. Create new Jupyter notebook. We're going to go ahead and save this to this same I guess it's a JSON file. That sort of makes sense. Phase 2 project. Yeah, okay. EDA 3, but are we doing dashes or underscores? We're doing dashes. File name, please make sure the file, blah, blah, blah. Oh, I need to select a kernel. .ipynb. Okay. Oh, here we go. A, B, C, D, E, F, Jupyter. Okay. Bro, how am I supposed to put the fucking file extension in there? So this is so like simple in fucking Jupyter Notebook, but Jupyter Notebook does so much stuff like over here that I can't have. So like it's really like, okay. What the fuck are we gonna do? Yeah, I know. Fuck, man. It like won't, when I go to like the drop down menu and to select like the right file extension, it doesn't have IPYNB available. What the fuck is this? No, fuck this. Bro, it should not be this fucking complicated just to make a single fucking IPYNB file in VS Code. It should not be this hard. What the actual goddamn fuck? The VS Code docs are completely fucking useless. God, how did I do that the first time? I hate this. I hate everything about this. I want to write code. I want to do math stuff. I don't want to fucking program. I want to do data science. I don't want to do fucking IT work. Why is there not a fucking IPYNB file extension? Oh, fucking great. Well, it's 3 years ago at least. Maybe it's not. No problem. There's some GitHub like error thing. This is completely not helpful at all. Okay. Stack Overflow for the win, hopefully. Open settings.json, change. Wow, okay. Control-Shift-P. He said open settings. What? Bro, oh my god! I'm about to fucking kick the fucking door down. Jesus, fuck this. Okay. Yeah, I would love to fucking save it, but I fucking can't, you fucking whore. Hey, buddy. Zeus doesn't like it when I get upset. Like, there should just be, like, a Jupyter notebook or, like, IPYNB in here somewhere. I don't even know what the fuck any is. Oh my god, dude. God, that is so fucking frustrating. Okay. I'm going to literally start Jupyter Notebook just to create a file and then fucking close it again. I would show you guys the screen here, but it's gonna take me like 2 seconds, so. It literally took that much effort. I could have done that all along, but like, why? Why can't I just simply create a new file with that file extension? What the like? Oh, there's so much like weird shit with VS Code. Like when it works, it's so amazing, but the 60% of the time that it's got some like weird IT shit going on, it makes me want to blow my fucking brains out. Come here, buddy. Come here. Hi. Yeah. It's okay. It's okay. You're a good boy, huh? Yeah. You're a good boy. I know. You're stressed out. Because I'm stressed out. It stresses you out, huh? Yeah. 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 Used to, he would avoid me when I would get angry, but at least now I think he like understands that I'm not mad at him when I'm like yelling at the computer screen. Obviously, like if he does something bad and I'm talking to him, he knows that he did something wrong, but he's kind of figured out now that instead of running away from me when I get that way, I actually calm down quicker when he comes up and hangs out with me. Mostly because I feel bad when he starts acting all pitiful. Yeah. Yeah, you act kind of pitiful, huh? You act kind of pitiful sometimes. Oh my goodness. Oh my goodness. Okay. Hi. Hi. So, with EDA 3, we want to what do we want to do? Adjust. What do we want to do? We want to transform the data. Better eliminate outliers. We want to transform for non-normality. We want to remove excessive features with excessive stats. Oh shit, you know what we didn't do in EDA 2 that we should have done? We should have checked out the Durbin-Watson score, which I should probably review what the Durbin-Watson score means. No, I'm pretty sure it's like a 0 to 4 scale, and you want it to be as close to 2 as possible, I think. Because it's like in the middle. The Durbin-Watson statistic is a test for autocorrelation in a regression model's output. The Durbin-Watson statistic ranges from 0 to 4 with a value of 2 indicating 0 autocorrelation. Values below 2 means there's a positive autocorrelation, and above 2 means there's a negative autocorrelation. Autocorrelation can be useful in technical analysis, which is most conservative, blah, 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 blah. This is Investopedia, so it goes on to talk about like how that relates to technical analysis when you're investing, which is a lesson for a different day. I'm not completely sure what autocorrelation is. Autocorrelation, sometimes known as serial correlation in the discrete time case, is the correlation of a signal with a delayed copy of itself as a function of delay. Informally, it is a similarity between observations as a function of the time lag. That's not what I'm looking for. Okay, here's the Investopedia definition. There's a lot of stat stuff in finance, so a lot of times the information on Investopedia is pretty relevant to what I'm doing here. Autocorrelation represents the degree of similarity between a given time series and a lagged version of itself over a successive time intervals. Autocorrelation measures the relationship between a variable's current value and its past values. An autocorrelation plus 1 represents a perfect positive correlation, while an autocorrelation of negative 1 represents a perfect negative correlation. Technical analysts use autocorrelation to measure how much influence past prices for a security have on its future price. I have a rough understanding of what securities are, so that mostly makes sense. As opposed to like options and whatnot. Anyway, all that to say, we want to come back here, whoops, and look at our Durbin-Watson score, 1.993. So I still don't know what that, because the reason you check the Durbin-Watson for what I'm doing is to check for homoscedasticity, which is basically like you might have like a linear pattern where it's just kind of scattered all over the place, so you can see stuff generally kind of goes this way. The more homoscedastic that it is like the more obvious of like a line it's going to create. So my intuition is that the more obvious that line becomes, the closer the Durbin-Watson score gets to 2. But I don't know that for sure, so we're going to investigate. Homoscedasticity, Durbin-Watson score. This is the same article I was just looking at. That's not what I'm trying to find. Oh my god. Relation to Durbin-Watson score. Testing the assumptions of linear regression. Here we go. That's a lot of words. Durbin-Watson statistic provides a test for significant residual autocorrelation. Okay, so the residual is like the distance of like a data point to the regression line. At lag 1, the DW stat is approximately equal to 2, 1 minus A, whereas A is the lag 1 residual. So ideally it should be close to 2, say between 1.4 and 2.6 for a sample size of 50. Minor cases of positive serial correlation indicate that some of the fine-tuning in the model, some room for fine-tuning in the model, consider adding lags of the dependent variable under lags of the blah, 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 blah. Violations of homoscedasticity make it difficult to gauge the true standard deviation of the forecast errors, usually resulting in confidence intervals that are too wide or too narrow. In particular, if the variance of the error is increasing over time, confidence intervals for out-of-sample predictions will tend to be unrealistically narrow. Heteroscedasticity may have the effect of giving too much weight to small subset of the data, in the subset where the error variance was largest when estimating coefficients. How to detect. Look at plots of residuals versus time, and residuals are blah, 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 blah. That's a lot of parentheses. Either it's a function of time or it's a function of the predicted value. Okay, so all that to me basically means that the Durbin-Watson score is not something to worry a whole lot about right now, because it's pretty fine. That, I don't know why, but somehow that makes sense to me, because the adjusted R-squared value is the same as the R-squared value. And I know what skewness and kurtosis are, but I don't know exactly what these values represent. So let's review that real quick. Skewness value. So skewness is like how far the mean is from the median. So instead of being normally distributed like a perfect bell curve, it might be to like the right. So your mean will be like the peak of the hump, but your median will be halfway between like the max and minimum value. Okay, a skewness value greater than 1 or less than -1 indicates a highly skewed distribution. A value between 0.5 and 1 or -0.5 and -1 is moderately skewed. A value between -0.5 and 0.5 indicates that the distribution is fairly symmetrical. So that means that this is way skewed. Let's include that in our observations. Whoops. The model as a whole presents in a extreme skewness, and I feel like that kurtosis value is like through the roof. I think kurtosis is supposed to be like 5 or something. Yeah, okay. Kurtosis is a measure of the combined size of the two tails. So I think it's like 1 standard deviation from the extremes. It's like 1 standard deviation in from the minimum and the maximum, whatever the area under that section of the curve is combined. It measures the amount of probability in the tails. The value is often compared to kurtosis of the normal distribution, which is equal to 3. Wow. So that means that we got some fat tails. Huh. So that means there's probably not much of a taper in our data. And this is like a multi-dimensional like regression model, right? So we're not looking at like, you could conceivably visualize up to 3 predictors with hold on. So you have like 2-dimensional, you have your predictor and your variable, or your predictor and your constant, I mean. And then you could have another predictor in like 3-dimensional. Yeah, so you can't really visualize more than like 2 predictors to 1 constant at a time. The house price is the constant. That's what we're trying to predict with our predictors, which are our features. So what was I getting at? Oh yeah. So the skew, like imagine we have one predictor and one constant, you know, and like ideally we have a perfect bell curve. Skewness is like how much like the hump is, like how not symmetrical it is, right? So if you have a skewness of I think 1, what did I say a minute ago? Between 1 and -1, so you want it around ideally 0, like right at 0. I keep losing my train of thought. I might need to take a break here in a minute. So you can understand that visually for like 1 or 2 predictors, like a 2-dimensional and a 3-dimensional plot. I don't ever make 3-dimensional plots, but you could. 4, 5, 6, 7. Like basically every feature you add into it is another dimension, and obviously you can't like visualize that. So that's why it's important that we have these numbers here rather than like a visual representation. So the fact that we want this to be as close to 0 as possible. So the fact that it's greater than 1 is a huge red flag, basically. It means our data is very, very not symmetrical, and it's left skewed, meaning the hump moves to the right, so to speak. We're dealing with multi-dimensions here, so it's not a clear right side of the graph, but you kind of get what I'm explaining. And so this is the area under the curve of our tails. The fact that we have a ton of features makes that kind of make sense. It's still a huge number. Absolutely massive. So for the standard normal distribution, which is the perfect bell curve, it's like 3. So the model as a whole represents an extreme skewness, and as well as kurtosis, urtosis. These statistics should reduce as the model improves. Skewness should move toward 0. At least below 1. It's just going to be a whole sentence on its own. And kurtosis should move towards 0. Okay. Skewness and kurtosis oh my god. At least below 0. And kurtosis should get as close to 3 as possible. This would indicate the data distribution finding a more normal shape. The Durbin-Watson score is nearly perfect which I find suspicious, to say the least, considering, how do I put this kindly? Look at me trying to be professional after just calling my computer a whore 5 minutes ago. Sorry about that, anyone that was watching. Sometimes you just gotta get mad at the computer, it's okay. Or VS Code, or Microsoft. What's a good word here? Obnoxious lack of normality amongst all the features. Okay. I'm gonna comment this out too, because if I ever like run this whole notebook again, I don't want that running because it's just gonna create another CSV file with the same name, and I don't even want to know what kind of errors that's gonna throw. It would probably just replace it, but what, I just don't want to do that. Anyway, save. Okay, EDA2 is more or less complete. I'm going to take a quick bathroom break, and I'll be right back. Don't go anywhere without me. Come on, squish, squish, squish. Squish, squish, squish. Okay. I wonder how long this stream's been going on for. I've completely lost track of time. It's over here. Let's close these tabs. Warning, please check the video. Oh, hey, we had a viewer for 34 seconds. Wow, can I get like... Man, a guy commented on my stream and I didn't respond, so... I feel kind of bad. He said he wanted to tell me something. Almost 2 hours? We've been doing this almost 2 hours. That's crazy. Okay. Hi there. Oops. Oops. What is all this? I'm not even looking at VS Code right now, by the way. I'm just looking at the stream stuff. Enable DVR. I don't even know what that means. Unlist live replay once stream ends. I don't want to do that, I don't think. Yeah, let's do live chat. And man, I would really like a ding or something when people message. Anyway, back to the project we go. We might go back to EDA2 real quick. Because I want to check the mean squared error. Which I believe I have imported. And the absolute error, okay. Not that I should remember what that's for, but I don't off the top of my head. But that's why I have notes, right? So that's the mean of all residuals, the mean absolute error, okay. What's the prefix for that method call? I don't think I need to because I imported that function directly. Good, okay. So I can just do mean absolute error. And Python should know what I'm talking about. Yeah. Yeah. Y true, Y predicted. I always think I'm ready to go to the next step, and then I come up with something else that I forgot about. Mean squared error. Learn. Oh my god, I just want to see some example code. Everybody wants you to read their docs and whatnot, which is like good sometimes, but I want to see like an example. Okay, here we go. So I just pass in like the true y values versus my predicted y values. Which I don't think I have. Not like in a callable way. Okay. Oh, I know this isn't that complicated, and then my brain's just like frying. I might have to. I'm probably just gonna take a walk here in a minute. That usually kind of helps me reset. So Python predict regression. Oh my god, okay. I don't think I have like a regression line declared though. It's all just like packed into the model. Model.predict. Okay. See if that works. Haha! Wow. Mean absolute error equals, I'm going to call that MAE. And then we want our mean squared error. Mean of squares of residuals. Mean don't think that's what I want. That. Do we have NumPy imported? Please tell me we have NumPy. Okay, good. np.squirt MSE print mean squared error whoops. Absolute now mean squared error. Let's see. Root mean squared error. That's a lot of letters, but whatever is RSE. Okay. And I have no real clue what any of this really means. Like how to interpret these numbers. So mean squared error interpretation. When a model has no error, the MSE equals 0. As model error increases, its value increases. Yeah. For example, in regression, the mean squared error represents the average squared residual. Okay. So that tells me something. It basically means that my data points are miles away from my regression line. Which is not awesome. But also just dropping some outliers from the data might help that out quite a bit. One way to assess how well a regression model fits a data set is to calculate the root mean squared error, which is a metric that tells us the average distance between the predicted values from the model and the actual values in the data set. The lower the RMSE, the better a given model is able to fit a data set. The formula to find the root mean squared error is blah, 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 blah. Where is it? Blah, blah, blah. The following examples, how does RMSE for a given regression model are as follows. Okay. So I don't think it matters a whole lot, or doesn't mean a whole lot what the mean absolute error and the mean squared error is. What really is the useful thing to know there is the root mean squared error. which is more or less a measure of spread for your residuals and not your data itself, but like the residuals, which are the distance from any given data point to the regression line. So what this basically means is that on average, oh my god, a given data point is about 234,000 units above or below the predicted value, which is the regression line, if you drew like a straight line to it. So no surprise here. Basically, like everything else we've seen so far, it's telling us that the data set that we pass into the model is complete trash. Or, well, to be more specific, the linear regression, the model that we're using does not fit the data set, like, at all. So we're going to have to tune the data set a bit. To make it fit. The root mean squared the root mean squared error is astronomical, which means it is probably worth looking into standardizing the units across features. My intuition is that this is at least in part due to there being so many different units of measurement used in the data set. So we have like one hot encoding, and then we also have like, well, okay, so specifically with the continuous variables. Units of measurement used among the continuous Is that how you spell continuous? Will it auto check me? No, it won't. Continuous. That also looks weird. It is the UOU. Weird. Okay. Okay. So that was a lot of work that didn't really tell me anything I didn't already know about the data, but I guess it did give me some ideas of what to do about the data that I didn't already have. So wasn't a complete and total waste of time. So because I'm very lazy, we're gonna just copy and paste this into EDA3. Standardize for units of measurement, and we're going to make this I want code. What the heck? gonna take like 30 seconds. I got like $10 says it takes 30 seconds to import all this. Normally it'd take like 5 if it wasn't streaming. That's okay. But it's got the syntax highlighting, but it's still going. Still going. Called it. 31.4. I called it. I told you so. Why is pipeline? Okay. Cool, man. Well, that was kind of everything I wanted to get done with this session. We did the finishing touches on EDA 2. We got started on EDA 3. Well, not really started on it, but we kind of prepared our notes and everything for EDA 3. As far as EDA 2, we've kind of beaten that dead horse to a pulp. But we have some, like, what's the word? Articulatable observations about the data now. I can at least, like, I put into words what needs to be changed about the data in order for it to, like, maybe fit into linear regression. So that's actually really encouraging. For most of this project, I've felt like I've just been, like, kind of throwing random stuff at the wall and seeing what works. Now I kind of have some sense of orientation, what I have to do in order to produce my deliverables for the project. So I'll probably get working on EDA 3 later tonight, but I'm going to have to write a blog for this project too, so I'm probably going to go ahead and start working on that, because I blogged the first one just like on LinkedIn. I'll probably do that again, like a non-technical blog, but then I want to also have like a technical blog on like an actual website. So yeah, cool. All right, well, I think that's it for the stream. That's really cool that we actually got, oh, hey, we got a like. Wow. That's really neat. Oh, hey, we got another viewer for a few seconds. They, oh, hi. I don't know if you're still here, Foxy, but thanks for joining. What is concurrent viewers? Who's this? Ooh, I don't want to do that. Thought I was gonna be able to like them or something. Okay. The stream's current bitrate is higher than the recommended bitrate we recommend. Okay. Anyway, we're gonna end that stream here today. I'm starting to get kind of like the hang of the whole streaming thing, so I'm probably gonna start doing this more regularly. So if there's no one watching right now, but if there's anybody playing this back later, go ahead and like, subscribe, do all that stuff. Put the notification bell on so that next time I'm start a stream, you can see what's going on. Cool. So I don't know if I should end the stream on Streamlabs first or on YouTube. Probably Streamlabs first because there's a little bit of a lag. Yeah. That's not the end of the world if it doesn't work out anyway. All right.